In the previous lecture on phonon, we have seen that phonons are actually the quantum or particle of lattice vibration, or you can say these are actually the quantum of elastic waves. Just like photons are the quantum of electromagnetic wave, in the similar manner we simply say that phonons are the particles uh, which uh, which is the which is the building block of elastic waves. And we have also seen that the energy of phonon is quantized, and so we say that the energy of lattice vibration or the elastic wave is quantized. So quantization of lattice vibration we have seen in our first lecture on phonon. Now today in this second lecture on phonon we are going to see the concept of momentum of phonon, or you can also say that what is phonon momentum we will see in this lecture. Okay. Actually a phonon has not a physical momentum in case of lattice, but as a phonon interacts with elementary particles like photons, like neutrons and electrons, so this interaction gives a proof or gives an evidence for the momentum of a phonon. So if you consider that there is a phonon having wave vector k, then this phonon just behaves like a particle with momentum given by p equal to h bar k. This particle appears like a particle having momentum h bar times k. Okay. Actually this relation p equal to h bar k, which represents the momentum of a phonon, this is in accordance with the de Broglie relation. You have definitely studied in your quantum mechanics course the de Broglie hypothesis that all material particles possess wavelength, has wave character, and the wavelength of a material particle is related to its linear momentum. And this result actually de Broglie has obtained on the basis of photon analogy. Okay. So we know in accordance with de Broglie relation the momentum p of a particle is given by h divided by lambda, where you know h is Planck's constant and lambda is the wavelength associated with the particle. Okay. Now in terms of the reduced Planck's constant h bar, you know h is equal to 2 pi h bar. Okay. So instead of h you can write 2 pi h bar. So p will be equal to 2 pi h bar divided by lambda. Okay. But you know this 2 pi over lambda is what? This is the magnitude of the wave vector k. So instead of 2 pi over lambda we can write k. So p is equal to simply h bar times k. This is the magnitude of the momentum of a particle. Okay. Behaving like a quantum particle. Actually this result holds for phonon, and a phonon behaves like a particle having momentum equal to h bar k in magnitude. And if your aim is to write down this expression in vector form, you can easily write that vector p is equal to h bar times vector k. So it is clear that the momentum of a phonon is in the direction of the wave vector k. Okay. So in this way a phonon you can say behaves like a particle having momentum h bar k. Okay. Now actually this momentum of phonon is also known as crystal momentum. Okay, sometimes we say that h bar k is crystal momentum. Okay, and actually, as I have told you earlier, that in a lattice, phonon does not carry any physical momentum except for k equal to 0. When k is 0, it means then there will be a uniform translation of crystal as a whole. Okay, so except this condition k equal to 0, momentum of a phonon is not physically has not a physical evidence. Okay, but for most of the practical purposes, we consider that a phonon behaves like a particle having momentum h bar times k. So finally, we conclude that you can treat phonon as a particle which is a boson, as you have seen in the previous lecture, and its momentum is h bar k, which is just equivalent to the momentum of a photon. Okay, but in Newtonian mechanics you can't define the momentum of a phonon or photon, but in quantum mechanics we always associate momentum with a phonon, and that momentum is equal to h bar times k. Okay, so remember it, whenever you talk about the momentum of a phonon in a particular physical process, then you have to consider or you have to imagine that phonon is nothing, it is a particle having this momentum h bar k. Okay, but now we will see how we can give the physical evidence of this momentum, why it is needed, why we have to consider that momentum is associated with phonon. So now let us see its physical significance. Okay, actually the physical significance of this momentum h bar k is provided by the momentum conservation laws or the wave vector selection rules, which determine the allowed transition between the quantum states. Okay, when there will be a transition of our lattice from one quantum state to another, then we must take into account the either the creation or the absorption of phonon. Only then momentum conservation will be valid and energy conservation will be valid. So to validate the momentum conservation law and the energy conservation law in most of the physical processes, we have to assume that either a particle like phonon is created or absorbed, and when you will consider that the particle has a momentum h bar k, only then you can see the momentum conservation and the energy conservation will hold good. Okay, so in this regard, now we consider the two examples or two cases. First one is elastic scattering, which is also called Bragg's diffraction or Bragg's reflection. At the for the term diffraction, you know, Bragg has used the term reflection, but when you say Bragg's reflection, that means actually diffraction of X-rays. And you have already studied in very detail Bragg's reflection or Bragg's diffraction in my previous videos. Okay, and you have seen that when an electromagnetic radiation, which is composed of photons, are incident on a crystal, they suffer actually the Bragg's reflection. Okay, and in that Bragg's reflection is actually the elastic scattering of photons by a crystal. Okay, in fact, when you talk about the elastic scattering, actually in that condition there is no loss of energy. Okay, no loss of energy, and so in this process actually neither a phonon is created nor a phonon is absorbed. So whenever you talk about the Bragg's reflection of X-ray by a crystal, then there will be no need of considering a phonon. So in this process, phonon's energy and phonon's momentum are not involved. Okay. So in Bragg's reflection of X-ray by photon by a crystal, that is governed by a particular wave vector selection rule, and you have already studied this selection rule when I have discussed the Bragg's reflection and reciprocal lattice. Bragg's law in terms of reciprocal lattice you have already studied, and in that video you have seen that the wave vector selection rule for the elastic scattering of X-ray photon by a crystal is given like this. This is kappa dashed is equal to kappa plus g. Actually here this kappa is the wave vector of the incident photon, and I have shown here, you can see this is the wave vector of the incident photon, and this kappa dashed, this is the wave vector of the scattered photon. Okay, and g, what is this g? You know it. This is actually the reciprocal lattice vector. So you have seen earlier that the selection rule governed by the wave vector in case of Bragg's reflection is given by this relation kappa dashed is equal to kappa plus g. Okay. Now if you are you want to know about the law of conservation of momentum, how you can express it. Actually for this, let us just multiply this equation number 2 both sides by simply by h bar. So when you will multiply equation 2 by h bar, your result will be like this. This is h bar times kappa dashed equal to h bar times kappa plus h bar times g. But you know, h, if we consider that h bar kappa, this is actually the momentum of a photon, not of a phonon. Here no phonon is created or no phonon is absorbed. So h bar kappa, this is actually the momentum of the incident photon, and this h bar kappa dashed, this is the momentum of the scattered photon, and h bar g, this term is added to for holding the conservation of momentum, where g is reciprocal lattice vector. So the conservation of momentum yields this equation. Okay. Now in this case, as there is no loss or gain of energy, so the energy of the incident photon, which is given by h bar omega ph, and energy of the scattered photon, which is given by h bar omega dashed ph, both will be equal. This equation represents the conservation of energy. Here actually this omega ph, you know, this is frequency of the incident photon, and omega dashed ph, this is frequency of the scattered photon. So you can see in this case neither a phonon is created nor a phonon is destroyed or absorbed. Okay. So you can say that in an elastic scattering of photon by a crystal, a phonon is neither created nor absorbed. Okay. Actually in this process, our crystal as a whole recoils with a momentum minus h bar g, minus h bar g. This is the momentum of the recoiling crystal. And from this equation number 4, it is easy to see that the omega prime ph is equal to omega ph. It means the frequency of the scattered photon is equal to frequency of the incident photon. So there is no change in frequency when Bragg's reflection takes place. Okay. Actually this process is called normal process or N process. So if in an scattering process there is no change in frequency after scattering, that means the frequency of the incident photon is same as that of the frequency of a scattered photon, then that very process is called normal process. Okay. So you can see that in case of elastic scattering of photon by a crystal, or in case of Bragg's reflection, neither a phonon is created nor a phonon is absorbed. Okay. But if you talk about an inelastic scattering of photon by a crystal, then what will happen? How in that condition you can say that energy conservation holds and momentum conservation holds? Actually, for the validity of energy and momentum conservation, you must have to assume that a phonon is either created or a phonon is either destroyed or absorbed. Only then these conservation laws will hold good. Okay. So now let us see what happens in case of inelastic scattering. Actually, in this case, there are two possibilities. In first possibility, we consider the creation of a phonon. Okay, you can see this figure. In this figure, I have shown that this a small, very small sphere. This is the scattering center. This is the crystal, or you can say this is the lattice. Okay, which acts like a scattering center. Okay, and on this scattering center or this lattice or crystal, a photon has been shown to be incident on it, and this kappa is the wave vector of this incident photon. And when this photon is interacted with the crystal, it gets scattered. Okay, and so this kappa dashed represents the wave vector of the scattered photon. Okay, but at the same time a phonon is created, and that phonon has a wave vector equal to this k. K is the wave vector of the phonon. Okay, in this case, if you will not consider that a phonon is created, then the selection rule or the conservation principle of the wave vector, conservation principle of momentum, conservation principle of energy will not hold good. These conservation laws will hold good only when we consider that in this process a particle called phonon having momentum h bar k or wave vector k or energy h bar omega is created. Only then these conservation principle will hold good. So for dealing with the inelastic scattering of photon with a lattice, we must consider that a phonon of wave vector k is created. Okay, and if we assume that there is a creation of phonon of wave vector k, then the conservation law for the wave vector or the selection rule for the wave vector can be expressed like this. This is expressed as k plus k dashed, kappa dashed is equal to kappa plus g, where you can see this k is what? This is the wave vector of the phonon, produced phonon or created phonon, and kappa dashed, this is the wave vector of the scattered photon. Okay, this kappa is the wave vector of the incident photon, and g is the reciprocal lattice vector. Okay, so this equation 5 represents the selection rule or the conservation law for the wave vector in case of an inelastic scattering of a photon with a lattice or with a crystal. Okay, now if your aim is to express the momentum conservation law, you can simply multiply this equation 5 with h bar. When you will multiply equation 5 with h bar, then you will get an equation which actually gives the momentum conservation. So the momentum conservation yields like this. This is h bar k plus h bar kappa dashed equal to h bar kappa plus h bar g. This equation actually gives the momentum conservation law. And in the similar manner, we can also write the equation for the energy conservation. So, and energy conservation is written like this. You can see this is h bar omega dash ph plus h bar omega equal to h bar omega ph. Actually here, this omega dashed ph, this this is actually the frequency of the scattered photon. Okay, omega is the frequency of the phonon. Okay, and omega ph, this is frequency of the incident photon. So what is this h bar omega dashed ph? This represents the energy of the scattered photon. H bar omega, this is energy of the phonon. Okay, and h bar omega ph, this is energy of the incident photon. So you can see the total energy of the particles after scattering, that is energy of photon, scattered photon, and energy of phonon, when get added, that will be equal to energy of the incident photon. This is energy conservation. So energy of the incident photon is splitted into two parts. The first part of this energy is the energy of a scattered photon, and its another part appears in the form of energy of the phonon. Okay, so this is the energy conservation law. Now we will see the another case of the inelastic scattering of X-ray scattering by a crystal, and this is the case of absorption of a phonon. Actually in this case, instead of creation of a phonon, there will be an absorption of phonon. You can see this figure. Here I have shown that this small sphere is actually our lattice or crystal, on which a photon of wave vector kappa is incident, and at the same time we also assume that a phonon of wave vector this k is also incident on this lattice. Okay, and this phonon get absorbed, and after that a scattered photon appears whose wave vector is kappa dashed. Okay, here there is an absorption of photon. So if your aim is to write down the conservation law for the wave vector, or the selection rule for the wave vector, how you can write? In fact, in this case, you can write the conservation law for the wave vector in this manner. Kappa hat, this is actually the wave vector of the scattered photon. That will be equal to what? That will be equal to this kappa plus k and plus reciprocal lattice vector. Okay, so kappa hat, kappa dashed is equal to kappa plus k plus g. Okay, k is the wave vector of phonon, kappa is the wave vector of incident photon, g is the reciprocal lattice vector, and this kappa hat, this is actually the wave vector of a scattered photon. Okay, now you can also find the momentum conservation equation, and that can be easily obtained simply multiplying equation 8 by h bar. Okay, h bar. So the momentum conservation yields like this: h bar kappa dash is equal to h bar kappa plus h bar k plus h bar g. Okay, this is the momentum conservation equation. And in the similar manner, you can also write down the energy conservation equation. Here, the sum of the energy of the incident photon and the incident phonon will be equal to energy of this scattered photon. Okay, in this case. So you can see, I can write here h bar omega dash ph. This is what? This is energy of the scattered photon, and that is equal to h bar omega ph. This is energy of the incident photon, and h bar omega is the energy of incident phonon. The last term represents the energy of phonon. So you can see, if we not consider this h bar omega here, then h bar omega prime ph cannot be equal to h bar omega ph. Okay, so from this equation number 10 and this equation number 7, you can see that in case of this inelastic scattering of X-ray by crystal, the frequency of the scattered photon, that is omega dashed ph, and the frequency of the incident photon, that is omega ph, are not equal. So there is a change in frequency. You have seen, in case of elastic scattering, there is no change in frequency, and that process was called normal process or N process. But what you are observing here, you can see, in case of inelastic scattering, there is a change in frequency. The frequency of the scattered photon is not equal to the frequency of the incident photon. Actually, this process is called Umklapp. Mark this. This is called Umklapp. This is actually a German word, and it means flipping over. Flipping over means there will be a change in the frequency. Omega ph is changed to omega dash ph. Okay, so this process in which frequency of the photon changes, this is called Umklapp, which means flipping over. Okay, or you also call it U process. As a normal process is called N process, this Umklapp is called what? This is called U process. Okay, so finally you can see that in inelastic scattering, if either a phonon is created or a phonon is absorbed, in addition to the Bragg's reflection, and the momentum is transferred to the crystal as a whole. So in fact, in this case, the momentum of the phonon appears as the momentum of the crystal, and so the momentum of phonon is also known as crystal momentum, which I have told you earlier. So I think now you have a clear-cut idea of the momentum of a photon. In brief, I am just repeating two facts. Physically, it appears that phonon has no momentum, it has no physical significance. But there are so many phenomena, like you have seen inelastic scattering, where we must have to consider the existence of phonon. We must have to consider that there is a particle whose momentum is h bar k. So whenever we consider the interaction of this phonon with the other particles or any other scattering center, then we must consider that phonon behaves like a particle with momentum h bar k, and photon has also the same momentum, you know it. So the expression for momentum for a phonon and that for a photon are same. H bar k represents the momentum of a phonon and also the momentum of a photon, where k is the wave vector associated with those particles. Okay, thank you very much.